Welcome back, future Cambridge scholars. If you are tackling the 0606 additional mathematics syllabus, you already know that these exams are a marathon, not a sprint. It's all about pacing yourself and managing your energy for the long haul. Today, we are diving deep into a topic that completely drains the time and energy of unprepared students: logarithms and exponential functions. We're going to use an incredibly mind-bending puzzle, the ancestor paradox, to master these concepts. By the end of this masterclass, you'll be able to decode command words, apply the right frameworks, and stop leaving easy marks on the table. So let's get right into the strategy. To get our mathematical gears turning, I want you to imagine a classic, complex exam-style scenario, but with a historical twist. Think about going back roughly 1,000 years in time. Based on a conservative assumption of one new generation every 30 years, exactly how many direct ancestors did you personally have living in the year 1000 AD? Just pause and really think about that for a second. We all know we have 2 parents, 4 grandparents, 8 great-grandparents, but what happens when you have to push that logical progression backwards for a full millennium? This is exactly the kind of escalating data question Cambridge loves to throw at you to test your pacing. Let's break down the data to find the trend, just like we would in a paper. 30 years ago, you had 2 parents. 60 years ago, 4 grandparents, which we write as 2 squared. 90 years ago, 8 great-grandparents, or 2 to the power of 3. And 120 years ago, 16 ancestors, which is 2 to the power of 4. The pattern is crystal clear. For every 30-year period, your number of direct ancestors perfectly doubles. You are looking at a classic geometric sequence. Now, the math is simple enough right here at the start, but the sheer speed at which this exponential sequence builds is going to become a massive roadblock if you try to brute force the calculation. Because look at this. If we keep projecting backward to the year 1000, we eventually hit a wall. We have to figure out how far back we need to go to find over 1 billion direct ancestors. Mathematically, you're being asked to find the smallest value of n, where 2 to the power of n is greater than 1 billion. I see students all the time, let's call them the Alexes of the exam hall, who overload their brains trying to use trial and error, just blindly guessing powers of 2 on their calculator. It's a huge waste of time. We need the proper mathematical tool to isolate that exponent quickly. And before we reveal that exact tool, I need to remind you, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's map out our strategy to secure these marks. We've just set up the ancestor paradox to show how fast things grow. Next, we'll clearly define what logarithms are. Then, we'll unlock the laws of logarithms, your ultimate cheat codes. After that, we'll tackle the infamous exponential e. And finally, we'll put it all to the test with a classic real-world decay problem. So let's fundamentally shift how we look at indices. Notice the comparison we have here. On one side, we have standard exponential form, 2 to the power of 3 equals 8. On the other side, we've beautifully rewritten that exact same mathematical truth as a logarithmic equation. Log base 2 of 8 equals 3. A logarithm is literally just asking a question. To what power do I need to raise the base number 2 in order to get the number 8? The answer, of course, is 3. Logarithms are the ultimate tool because they allow us to pull the unknown right out of the exponent so we can actually work with it. The absolute key to mastering this is understanding your base. In the general expression log base a of x, that tiny base a is simply the number we are raising to a power. Now, technically, you can use any positive number as a base. But when you are sitting in that exam hall, staring at your scientific calculator, you're generally going to rely on 2 specific buttons. There is base 10, which is often written as LG or just log, and then there is base 2.718, a very special mathematical constant known as e, which gets its own button written as ln, or the natural logarithm. To actually solve complex Cambridge questions, you need to know the rules of the game intimately. These are the 3 primary laws of logarithms, and they are your absolute best friends. Number 1, the multiplication law. The log of x times y splits into the log of x plus the log of y. Number 2, the division law. The log of x divided by y becomes the log of x minus the log of y. And number 3, this is the absolute game changer for our billion ancestor paradox, the power law. The log of x to the power of n equals n times the log of x. The incredible thing to remember here is that these aren't just random rules to memorize. They are the exact same rules as the laws of indices, just written in a different language. Let's see this strategy in action, transforming a seemingly stuck equation into full marks. Let's say your paper asks you to solve 3 to the power of x equals 2000. How do you extract that x? Step 1, you systematically take the log of both sides. Let's use base 10. So lg of 3 to the power of x equals lg of 2000. Step 2, you deploy that power law we just highlighted. You grab that unknown x from the exponent and bring it right down to the front. Now you have x times the lg of 3 equals the lg of 2000. Step 3, it's just basic algebra now. Divide both sides. X equals the lg of 2000 divided by the lg of 3. Punch that into your calculator, and you get exactly 6.92. No rushing, no guessing, just a flawless, systematic extraction of the right answer. Now that we've got a handle on logs, we have to look at their mathematical mirror image. When you see the logarithmic function y equals log base a of x and the exponential function y equals a to the power of x, you need to recognize instantly that they are exact mathematical inverses. They effectively undo each other. If you were to sketch them on a graph, they would be perfect symmetrical reflections across the diagonal line y equals x. Remember this golden rule for your exam pacing. Whenever you are trapped in an exponential problem, you take a logarithm to escape it. And whenever you are stuck in a logarithm, you use an exponential base to break free. And when we talk about exponential functions in the 0606 syllabus, there is one undeniable heavyweight champion you must know. It's known formally as the exponential function, written as y equals e to the power of x. Remember that natural logarithm ln button we talked about? Well, e is its base. The letter e stands for a specific, naturally occurring mathematical constant that is roughly 2.718. It might look messy and random, but trust me, e is the foundation of advanced math, physics, and biology. It shows up naturally any single time a quantity grows or shrinks continuously. The behavior of these functions on a graph is completely dictated by the sign of the exponent. When x is positive, the curve shoots upwards into the sky with terrifying speed. This is rapid exponential growth, exactly like the number of our ancestors doubling as we go back in time. But when x is negative, the curve swoops downwards. This is exponential decay. It drops rapidly at first, then slows down, flattening out as it approaches zero, but never actually touching the axis. And hey, speaking of growing rapidly, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's put our skills into a high-pressure, interactive workshop mode. Here is a highly practical, real-world decay problem that is an absolute classic in Cambridge past papers. You buy a second-hand car for $20,000. It depreciates, meaning it loses its value, at a rate of 15% each year. The command question is, after how many whole years will this car first be worth less than $10,000? This is where students who rush, let's call them the Sams of the world, lose massive marks because they misread the setup. We have to build an exponential decay model. Let's scan the data and visualize this depreciation perfectly. At year 0, the car is worth the full $20,000. After 1 year, it loses 15%. Now, pro tip, do not calculate 15% and subtract it. That wastes precious time. Instead, realize that losing 15% means it retains 85% of its value. So, 20,000 multiplied by 0.85 instantly gives us $17,000. By year 2, it retains 85% of that new value, dropping to $14,450. Because we are continuously multiplying by 0.85, the car's exact value after n years is elegantly represented by the expression 20,000 times 0.85 to the power of n. Okay, this is where we separate the top-tier grades from the rest. Let's solve the inequality to find out exactly when the value drops below half its original price. Step 1. Set up the inequality. 0.85 to the power of n is less than 0.5. Step 2, we take the log of both sides. Step 3, use the power law to bring n down to the front. Now, red alert, I want you to find the flaw that ruins so many exam papers right here in step 4. We need to divide both sides by the log of 0.85 to isolate n. But because 0.85 is a fraction less than 1, its logarithm is actually a negative number. The golden absolute rule of inequalities is that when you divide by a negative, you must flip the inequality sign. If you miss this, the examiner crosses your answer out in red ink. So, n becomes strictly greater than the log of 0.5 divided by the log of 0.85, which calculates to n is greater than 4.265. So n is greater than 4.265, but you must read the command word requirements of the question. It asks for the number of whole years. In this context, n represents the end of a discrete year. Since n has to be strictly greater than 4.265, the very first whole year where the value is definitively below the halfway mark is year 5. Your final full mark answer is exactly 5. This brilliantly demonstrates how mastering abstract logarithm rules allows you to completely dismantle a complex, real-world financial problem in under 2 minutes of exam time. Which brings us full circle, back to our opening paradox. This proverb beautifully reminds us of the profound human reality of our ancestry. But what about the math? If you follow the exponential growth back to the year 1000 AD, our logs dictate you should have well over 1 billion ancestors. But wait, the entire population of planet Earth back then was only a tiny fraction of a billion. So our initial rigid assumption was flawed. We don't actually have perfectly distinct family trees. Because of intermarriage over centuries, our family trees overlap massively. Logarithms didn't just give us a cold number today, they forced us to uncover a mathematically proven truth about how deeply connected humanity really is. Students who implement these exact mathematical strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here is your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you are facing right now. Our team responds to every single comment. Like and share this video with your study partner. Ace the Exams. Your Cambridge success starts here.